So, if you wanted to turn the Earth into a black hole, you wouldn't actually need to add any material to it at all.
Not a single thing.
Right. You would just have to take the entire planet, like every mountain, every ocean, every city, and, all 8 billion of us, and you just crush it down into a sphere about 9 millimeters across, basically the size of a glass marble.
Yeah, that is a terrifying visualization, honestly,
Voila.
but it perfectly illustrates the absolute extreme nature of the physics we are exploring today.
It really does. Well, welcome to today's deep dive. We are thrilled to have you with us. And to guide you through the most mind-bending, violent objects in the cosmos, we are actually using a remarkably grounded roadmap today.
Grounded is definitely the word for it.
Yeah. We have this highly detailed fifth grade STEM science fair research document. It's titled Gravity's Grip, Modeling Black Hole Gravitational Lensing. And the best part is, it was put together with a budget of about $60.
Which is just brilliant. I mean, because it strips away all that impenetrable jargon of astrophysics. It just leaves us with pure, observable mechanics.
Exactly. So, our mission today is to shortcut you to a profound understanding of black holes, general relativity, and how gravity fundamentally shapes the universe. By the end of this conversation, you will understand exactly what happens if you fall into the abyss.
Oh, that's always the fun part.
Totally. And you'll see how a cheap piece of stretchy spandex can explain the whole architecture of space-time. But to understand how you crush an entire planet into a marble, we first have to look at the unimaginable violence required to create a black hole in the wild.
Right. So we have to look at the life cycle of massive stars. And, massive is the key word here. We are talking about stellar bodies that are at least 20 times the mass of our own sun.
Wow, 20 times.
Yeah. A star of that size is essentially a billion-year-long wrestling match.
It's a balancing act between two opposing forces, right? Like, for a star's entire active life, it is burning nuclear fuel, just fusing hydrogen and helium in its core.
Exactly. And that nuclear fusion creates a colossal outward explosion. It's this constant pressure pushing radiation out into space.
And that outward push is literally the only thing fighting against the unimaginable, inward-crushing pull of the star's own gravity.
Right. And as long as the star has fuel, the wrestling match is a draw. The star remains stable. But eventually, the fuel runs out. The fusion flickers and stops.
So the outward pressure just vanishes?
It just vanishes completely. Gravity, which has been relentlessly pulling inward for millions of years, suddenly has no opposition at all. So gravity wins.
And the speed at which it wins is staggering. Okay, let's unpack this. The core of a giant star collapses in less than 1 second. Just picture that for a moment.
It's almost impossible to picture. Millions of miles of superheated plasma just suddenly in free fall.
Right. The outer layers crash inward, they hit that incredibly dense, collapsed core, rebound off of it, and then explode outward in a supernova.
Which is one of the brightest events in the universe. I mean, a single supernova can briefly outshine an entire galaxy of billions of stars. But while those outer layers are blasted into deep space, the core itself remains.
And because it's been crushed so violently, its density just completely defies common sense. It can become a neutron star.
Yes.
And to picture the density here, imagine taking a single teaspoon from your kitchen drawer and scooping up a spoonful of neutron star material. Here on Earth, that single spoonful would weigh 10 billion tons.
10 billion tons?
Yeah, the atomic structure has completely collapsed. The electrons and protons are literally smashed together into a soup of pure neutrons.
And that is just a neutron star. If the original star was massive enough, even the resistance of those neutrons isn't enough to stop the crush of gravity.
So the collapse just keeps going.
Exactly. It continues indefinitely, shrinking smaller and smaller until it forms a black hole.
And these come in a few different weight classes, right? You have your stellar mass black holes, which are maybe 3 to 100 times the mass of our sun. You have intermediate ones. And then you have the supermassive black hole.
Right, which are millions to billions of times the mass of the sun, like the supermassive one sitting right in the center of our Milky Way galaxy.
Ooh, Sagittarius and star.
Yes. And the research also mentions theoretical primordial black holes. Those are tiny ones formed by the chaotic pressure of the Big Bang itself. But regardless of their size, they all share a specific, bizarre anatomy.
They really do. And understanding that anatomy means leaving our everyday intuition entirely behind. So we mentioned the core, the singularity. Then there is the event horizon, the photon sphere, the accretion disk, and those relativistic jets.
Let's start with the outer rings and move inward. The accretion disk is often the only part we can actually see. It is a massive disk of gas, dust, and shredded stars swirling around the black hole.
But wait, why does it glow so brightly if it's orbiting a dark hole? I always think of it like water circling a drain, but instead of water, it's cosmic debris.
A cosmic traffic jam is actually an excellent way to conceptualize it. Because the inner tracks of the drain are spinning so much faster than the outer tracks, the particles are constantly smashing into each other.
So the sheer friction of that debris grinding together heats the disk up.
Exactly.
Yeah.
It heats up to millions of degrees. The friction is converting gravitational energy into immense heat and light, making it blast out X-rays and literally outshine entire galaxies.
Wow. And some of that superheated material doesn't even make it into the black hole, right?
Right. The extreme magnetic fields generated by this spinning dynamo take a portion of that matter, twist it up, and blast it outward from the black hole's poles at close to the speed of light.
So those are the relativistic jets, and they can shoot out for thousands of light years. But then, if we push closer, past the accretion disk, we hit the photon sphere.
Yes. This is a region where gravity is so intense that light itself is forced into a circular orbit.
Which is just wild to think about. If you could somehow survive standing in the photon sphere and you just look straight ahead, the light from the back of your own head would orbit the black hole and hit your eyes. You would literally see the back of your own head.
It is wild. And if you step just a bit closer, you cross the event horizon,
Mm.
which is the defining feature of a black hole.
That's the boundary where the escape velocity, the speed you need to break free of the gravitational pull, finally exceeds the speed of light.
Exactly. And since nothing in the universe can travel faster than light, nothing can escape. Not radiation, not information, nothing.
Which brings us to the center, the singularity. And I have to push back on this concept a bit because the material defines the singularity as having theoretically infinite density and zero volume, absolute zero.
Right.
But how can something containing the mass of an entire giant star have no physical size whatsoever? Does that even make physical sense? It feels like a mathematical error rather than a physical reality.
Well, you are actually hitting on one of the greatest unresolved problems in modern physics. When we say zero volume, it really means our current equations completely break down.
So it is kind of an error message.
Essentially, yes.
Mm.
General relativity cannot adequately describe a point of infinite density. It just gives us an error message. But while we cannot physically describe the singularity, we can describe the boundary around it.
The event horizon.
Yes. The mathematical perimeter of the event horizon is dictated by something called the Schwarzschild radius. It tells us how much we have to compress an object of a certain mass to turn it into a black hole.
Okay, so every object has a Schwarzschild radius.
Exactly. If our sun somehow collapsed into a black hole, which it won't, it doesn't have nearly enough mass, but if it did, its Schwarzschild radius would be about 3 kilometers across.
So you would be compressing an object that is normally over 1,000,000 kilometers wide into a sphere the size of a small town.
Right. And if we compress the Earth, we get that 9-millimeter marble from earlier.
Here is where it gets really interesting. This introduces a major conceptual problem. If a black hole is just a mathematical boundary with a singularity inside that has zero volume, there is no physical surface.
None at all.
There is no solid ground pulling you down. So to understand how it traps things, we have to completely rewrite our understanding of gravity. Isaac Newton's laws are no longer going to cut it. We have to bring in Albert Einstein.
Right, because Newton's view of gravity ruled the scientific world from 1687 until the early 20th century. He defined gravity as a force, an instantaneous attraction between two objects with mass.
Right, the whole apple and the earth thing. The earth pulls the apple down. It works beautifully for everyday life. Like we build bridges and fly airplanes using Newtonian physics.
It does. But Newton envisioned gravity as an invisible tether, like a direct magnetic connection. The problem is, when things get incredibly massive or move incredibly fast, Newton's math just falls apart.
Like with Mercury, right. It couldn't accurately predict the orbit of Mercury because it's so close to the immense mass of the sun.
Exactly. Then Einstein came along in 1915 and proved that gravity is not a force pulling objects through space at all. Gravity is the geometry of space itself.
He introduced general relativity, proposing that the 3 dimensions of space, so length, width, and depth, are permanently woven together with the dimension of time, creating a single 4-dimensional fabric known as space-time.
And visualizing a 4-dimensional fabric is a really quick way to give yourself a headache.
Oh, absolutely. But this is where the 5th grade science fair project provides the perfect tactile analogy to make this relatable. Imagine you take a piece of stretchy spandex fabric and pull it taut over a circular frame, like a drum.
Okay.
Now place a heavy bowling ball right in the center. The weight of the ball causes the spandex to dip, creating a deep funnel shape. The bowling ball represents a massive star, and the spandex is the fabric of space-time.
I love this model.
Me too.
Yeah.
Now, take a small glass marble and roll it nearby across the spandex. The marble doesn't travel in a straight line. As it hits the depression, it curves around the bowling ball. It's not being pulled by a magnetic force, it's just following the curve of the sheet.
What's fascinating here is the big so what. Because gravity is a curve in space, it affects everything traveling through that space, even things with absolutely zero mass like light.
Because in Newton's universe, gravity only works between objects that have weight. Light is made of photons, which are completely massless. So a beam of light should travel in a perfectly straight line.
But according to Einstein, massive objects warp the space-time around them, and smaller objects, or even photons, are just traveling along the straightest possible paths called geodesics through that curved geometry.
So if gravity is the curving of the road itself, then anything traveling on that road has to turn regardless of how much it weighs. A heavy truck and a feather both have to follow the curve of the highway.
Exactly. More mass equals a deeper curve, which means light bends more sharply.
So what does this all mean? This realization that light bends brings us directly to the core of the student's science fair project, gravitational lensing.
Right, and this is the ultimate test of Einstein's theory. If he was right, we should be able to see light bending around massive objects.
And Arthur Eddington famously proved Einstein right in 1919, right?
He did. During a total solar eclipse, the moon blocked out the glaring light of our sun, allowing Eddington to photograph the distant stars positioned directly behind it.
Because the sun's massive gravity was warping the space around it, so the light from those distant stars bent around the sun to reach Earth's telescopes.
Exactly. The stars appeared to be in a different position in the sky than they actually were. It was a cosmic optical illusion caused by gravity acting as a lens.
And the research details 3 specific types of this lensing. First, there is strong lensing. That's when a massive galaxy cluster sits directly between us and a more distant light source, creating giant visible arcs or even complete halos of light known as Einstein rings.
Yes. Then there is weak lensing. That one doesn't create visible rings, but rather tiny statistical distortions in the shapes of background galaxies. Astronomers analyze those to map out dark matter.
Because we can't see dark matter, but it has mass, so it bends light.
Precisely. And finally, there is microlensing. This is used for smaller wandering objects. If a rogue black hole or even an exoplanet passes perfectly in front of a background star, its gravity acts like a magnifying glass for just a few days. We just see a temporary sharp spike in the star's brightness.
Which brings us to the actual experiment in the 5th grade project. It's just so elegant. The students stretched spandex over a frame, placed different masses in the center, like a golf ball, a baseball, a heavy metal shot put.
And then they rolled a marble from a fixed distance.
Exactly 4 centimeters away, and they used a simple protractor to measure the angle of deflection. The hypothesis was straightforward, right? If the mass in the center increases, then the deflection angle of the marble increases.
It is a textbook application of the scientific method, the 8 steps from hypothesis to communication. They changed one variable, the central mass, and measured the resulting curve.
What I marvel at most are the extension ideas in the project. It's just brilliant to suggest replacing the rolling marble with a laser pointer.
Oh, to perfectly simulate a photon of light traveling across the warped fabric.
Exactly. If we connect this to the bigger picture, this exact method of observation and analysis is how NASA maps the invisible universe today.
It really highlights that the scientific method is the great equalizer. Between a 5th grader and a top astrophysicist, the logic is completely unbroken. You scale up the shot put to a supermassive black hole, and you scale up the protractor to global observatories.
And those global observatories have achieved some truly staggering milestones. We've modeled it with spandex and marbles, but what does it actually take for humanity to observe these phenomena in the real universe?
Well, the timeline is wild. We didn't even confirm the existence of a stellar mass black hole until 1971 with Cygnus X1.
And the leaps in technology since then are hard to fathom. Take the LEGO Observatory in 2015. They detected gravitational waves for the very first time, literal ripples in the fabric of space-time.
Caused by 2 massive black holes colliding and merging over a billion light years away. When those waves finally washed over Earth, they physically stretched and squeezed our planet.
But the distortion was microscopically small, right? I read the wave warped the observatory by a distance smaller than the width of a single proton.
It's absurd precision. Yet we measured it. And just 4 years later, in 2019, the Event Horizon Telescope project produced the first actual image of a black hole.
M87 star. A titan weighing 6.5 billion times the mass of our sun. And they had to link radio telescopes spread across 4 continents to do it, acting as a telescope the size of the Earth.
And in 2022, they used the same technique to image Sagittarius, a star located 26,000 light-years away in our own galactic backyard.
Which is incredible. But this brings me to the most unsettling part of this entire deep dive, the falling in scenario. I need you to explain this because it completely blows my mind.
Okay, let's hear it.
The research says that if you were to fall toward a black hole, an outside observer, like a friend watching from a safe distance, would see you freeze at the event horizon and slowly fade away. But you, the person falling, would feel absolutely nothing unusual as you crossed it. Imagine watching a friend freeze in time at the edge of a black hole. How is that even possible?
It does sound like sci-fi, but it is a direct consequence of a phenomenon known as gravitational time dilation. Remember that Einstein proved mass warps both space and time together.
Right.
A deep gravity well isn't just stretching the physical distance. It is literally stretching the passage of time itself. Time passes more slowly in stronger gravitational fields.
So if I am falling toward the black hole, I feel fine. My watch is ticking at a normal pace.
Exactly. To you, you just smoothly cross the event horizon. But for your friend on the spaceship, floating in weaker gravity, their time is moving much faster relative to yours.
Or my time is slowing down relative to theirs.
Precisely. As you get closer to the intense gravity, the light reflecting off your body has to fight incredibly hard to climb out of that well. To them, your movements appear to slow down to an agonizing crawl.
I picture it like trying to watch a live video stream on a terrible internet connection. Eventually, the video stream just freezes completely at the event horizon before fading to black.
A buffering video is a fantastic analogy. And the craziest part is this isn't just theoretical. It's so real that our everyday GPS satellites have to correct their clocks to account for it.
Wait, really? Because Earth has a mass, so it warps space-time too.
Yes. The gravity down here on the surface is slightly stronger than the gravity up in orbit. So the GPS satellites operate in weaker gravity. Their onboard atomic clocks literally tick faster than clocks on our phones.
So if engineers didn't program them to mathematically adjust for gravitational time dilation, the entire GPS network would become hopelessly inaccurate.
Within hours.
That is deeply profound. Every time you pull up a map on your phone, your location is being calculated using the exact same relativistic physics that causes a person to freeze in time at the edge of a black hole.
It really shows how consistent the universe is. From an app on your phone, to a marble on a piece of spandex, to this supermassive abyss at the center of a galaxy.
It totally puts things in perspective. This journey has taken us from a stretched piece of spandex to the very edge of the event horizon.
It really has.
We've learned that gravity isn't a pull, but the geometry of space-time itself, and that black holes are the ultimate expression of that geometry. But as much as we have managed to observe, black holes still hold mysteries, right?
They absolutely do. In fact, I want to leave everyone with one last mind-bending concept from the source material.
Oh, let's hear it.
We have spent this entire time talking about how black holes trap things forever. Nothing escapes. But in 1974, Stephen Hawking predicted something called Hawking radiation.
Okay.
It's the idea that black holes aren't entirely black. Through complex quantum mechanics at the event horizon, they actually slowly evaporate by emitting tiny quantum particles over astronomical timescales.
Wait, so they're shrinking like a puddle of water evaporating?
Yes. Given enough trillions of years, a black hole will evaporate into nothingness.
But that creates an insane paradox. If a black hole eventually evaporates into nothing, what happens to all the stuff, all the stars, the light, the information it swallowed over billions of years?
Exactly. It's called the black hole information paradox. If that information just disappears, it violates the core rules of quantum physics.
Wow. You start the day looking at a 5th grade science fair project made of sporting goods, and you end it questioning the fundamental conservation of reality itself.
A lot to think about.
I highly encourage you to mull over that paradox tonight. Thank you so much for joining us on this deep dive. Next time you drop something heavy on a stretched piece of fabric, just remember you are holding a model of the universe in your hands.